Good afternoon, or good morning, or good evening, depending on where you're joining us from today. I am Dr. Bethany Williams, and I'm the lead for training and education at the National Pathology Imaging Cooperative based in Leeds in the United Kingdom. And I'm really delighted to be able to join you all at the fourth session in our free digital pathology educational webinar series, Innovation into Practice. Now, the focus of today's session is digital pathology infrastructure and demystifying DICOM. This is a great opportunity for us all to brush up a bit on our IT and informatics knowledge and learn more about some of the challenges and opportunities involved in deploying digital pathology infrastructure over a regional network. We've got two fantastic speakers for you today, Mr. Basharat Hussain and Dr. Craig Sayers, who will be sharing all their knowledge and expertise from working on the NPIC project, and in particular on our regional and national deployment programmes. So as you may know, we sort of made it our personal mission over the last 5 years at Leeds and at NPIC to try and make digital pathology mainstream. So we've set out to try and answer some of the very fundamental questions that pathologists, biomedical scientists, IT professionals and laboratory managers might have about how to deploy digital pathology, particularly in clinical settings, safely and effectively. And we've gone out of our way to try and produce some easily accessible, pragmatic publications and events to help guide other departments in their digital journeys. So you may be familiar with the original Leeds Guide to Digital Pathology, which has now been translated into 12 different languages, including a USA version of the English language text. Do feel free to download that again. So that's a little old now, but it's still got lots of useful information about the first steps to undertake when you are starting a new deployment adventure. And we'll put a link for download to that in the chat just to help you. But in addition, we also now have the Leeds Guide to Digital Pathology Volume 2, and we're incredibly excited about this new publication where we delve a little deeper into some of the most sort of pressing topical topics regarding digital pathology deployment, including things like home reporting, multi-site digital pathology deployment and national networks, artificial intelligence, and patient and public involvement and engagement. So that's a really great resource. We've also got lots of sort of personal stories from different members of the team and different members of our laboratory team as well, talking about sort of how digital pathology has altered their working lives. So again, we'll put another link to that in the chat for you. So without further ado, let's move on to the main event today and our presentations from Bash and Craig. Now do remember you can put your questions into the chat and we'll have a nice lengthy Q&A session at the end of the presentations when you can pose questions to both of our speakers, and we'll try and get through as many of those as possible. Thank you.
Hello everyone, I'm Bash Hussain, Deployment Director responsible for the clinical deployment of digital pathology across our NHS partner sites. I've worked for Leeds Teaching Hospitals for over 7 years and I've been involved in the deployment activities from 2017. I managed the deployment at Leeds Teaching Hospitals, who went live with 100% surgical slide scanning back in 2018. I have a degree in computing and a background in project and program management. It's great to see so much interest from across the United Kingdom, but what's even more fantastic is to see that we have interest from all 4 corners of the globe. I hope you find the next 20 minutes or so really helpful and informative. What I'll begin with is a quick overview of the NPIC program. Just a reminder for those of you who have joined for the first time. I'll then lead into some details around the National Digital Pathology Platform and infrastructure. hopefully sharing with you some key considerations and decisions we took, which has got us to the point we are today. I'll then briefly touch on deployment experiences and some of the technical challenges we faced along our journey. The NPIC program aims are to deliver clinical use of digital pathology, which in effect is the deployment of scanners, the PAC system, infrastructure and storage, networking and integration, pathologist workstations, and to support the clinical use of the solution. With that foundation layer being in place, it will expedite our aims of being the place for AI development and evaluation over the whole life cycle and continue to support further research and innovation within this field. With regards to driving the use of digital pathology, there are three parts to this from a program outcome perspective. The first is to scale up 3 NHS improvement networks across the north of England, which supports up to 6 million people. That's 15 NHS trusts, over 200 pathologists, with 48 high throughput scanners scanning over 2.4 million images each year. The second outcome is to fully digitize the Royal National Orthopaedic Hospital and link up to 7 hubs to enable sharing of images. This will connect up to 50 pathologists across England, and NPIC will address the serious growing shortage of expertise in bone and soft tissue pathology in the country. The final outcome is to digitize Great Ormond Street Hospital, deploying to around 19 treatment centres and connecting 70 pathologists. NPIC will help to address the growing demands of expertise in paediatric pathology across the country. This slide shows the variety of work packages across the programme and also highlights our key industry partners who NPIC are working with in order to achieve the programme aims. So how did NPIC build the largest digital pathology platform for the NHS? Well, for the start, we managed to secure funding by multiple bids to various central government bodies. These bids were made in 2019 and 2020, and funding was secured just as the pandemic started, which meant we had to reorganize the team to work from home and press ahead with the new ways of working and a significant IT program of work in front of us. Having adjusted to the constant reminder of "you're on mute" and the never-ending rings of the doorbell, we managed to identify procurement routes for the provision of software and infrastructure. The outcome was Sectra and Exponentially were appointed at the end of 2021. The systems were built, configured and tested, resulting in a go-live last month. This is a very brief summary of some of the key considerations we had to take into account or decide upon in order to deliver our solution. How many organizations and the number of slides? This was a major influence on the scope of work and the overall size of the infrastructure. Organizations less so, but understanding slide or case volumes will help you cost out which pricing tier will be used. This is typically what software vendors use to price up Scanning magnification and image retention. I often see various options on this, 20x or 40x, and what is the percentage split? Usually to help reduce the cost of storage, but the percentage split is typically always leaning more towards 40x than 20x. We have agreed to scan all work at 40x. I have also had many questions about how long we will keep the digital image for. Some deployments, again, in order to save storage costs, will only keep images for a matter of months. The Royal College guidelines recommend keeping images for 2 lab inspection cycles. How much storage do we need? Depends on your scanning magnification. You'll see later on what we've put in place from a storage perspective. How many users access the system? This really links to how many pathologist workstations you need, and also how many medical grade displays you'll need to procure. How resilient does a system need to be? Well, there's always a glass slide, right? So any system interruption won't be so bad. Well, some sites around the world have stopped shipping glass out to pathologists. And in that case, the system resilience becomes more critical. You'll see what the NPIC approach is on resilience on the next slide. What level of performance do we expect? This is normally the pathologist experience when viewing the digital image, but it also links to workflow expectations. The data transfer between scanners and the storage repository is very important. We didn't want to be responsible for bringing our whole trust network down just because we ended up loading a few too many glass slides into the scanner at the same time. Single vendor or multiple vendors? We decided to appoint a software vendor for the PACS solution and a separate infrastructure vendor. We felt it provided us with more options and flexibility, as well as potential longer-term savings. To cloud or not to cloud? I guess that's the question. Well, we decided to go with an on-prem solution rather than cloud. As a cost buyer, our procurement exercise demonstrated that an on-prem solution for our requirements was much more cost procurement route to take and contract duration? Well, procurement is key, especially on high-value long-term contracts. For our infrastructure provider, we use G-Cloud 12 as a framework. What levels of integration? Well, integration is always key to a seamless workflow. Our ambitions are to ensure that tracking system, LIMS, which is a lab information system, and the PAC system are all integrated. But to be honest, it's easier said than done. This is the National Digital Pathology Platform, or a little diagram anyway. So NPIC have gone with a dual data center setup with multiple tiers of storage providing a high availability service which is resilient. The solution has a number of different tiers of storage. Alongside that, it also has a capability to connect into any cloud infrastructure in the future. So for example, if we wanted to archive into a cold tier of storage in one of the major cloud vendors' platforms, we're able to do that. Additionally, what's worth noting is any of our NHS partner sites have the ability to connect into this infrastructure. We prefer or we recommend a dedicated line, but there are the opportunities to also use the HSCN connection. Either way, we tend to find that having both options available provides additional resilience just in case there's a problem on one of the lines. It's worth noting that due to the procurement framework we used, G-Cloud 12, the security requirements on the infrastructure meet or exceed the expectations set out by NHS Digital. So we're really pleased about that. This is the high-level design that I thought is worth sharing, just to give you an oversight in terms of the overall picture. So initially, at the bottom, we've got the various different scanners. We use Leica, Roche, or Hamamatsu, but there are many other scanner manufacturers that are available and that can connect into our infrastructure. The second tier is the storage tier. So that complex diagram that I just showed you previously, in effect, is the storage layer for our infrastructure. And the third layer is a vendor neutral archive, also known as the sector pack system. I'm just highlighting the core elements of the overall solution: the scanners, the storage, and the sector pack system. So what does this mean? Dual data centers provide real-time replication of data and instant failover. There's 20 petabytes of storage across 2 data centers. And currently we can store over 7 million whole slide images. The infrastructure is scalable, and so is the storage, and we can have multiple exabyte levels of storage available. And just for you who haven't heard about an exabyte of storage, that's 1,000 petabytes. We also have the potential to capture and store all whole slide images across the UK for over 30 years. There's seamless site-to-site image sharing capability. So it means if you're part of the NPIC network, you can instantly access an image that's been scanned in a different hospital. There's potential to improve turnaround times for cancer diagnosis. And there's faster deployment of AI capabilities to all the NHS. And what that gives us is a vast capability from a research point of view and the ability to support clinical trials. What this also means is we have the potential to save the NHS a minimum of £100 million. And that's purely based on the fact if each hospital went and procured their own little digital pathology system, their own infrastructure, and their own storage. We've excluded the scanners because typically all sites will need to procure scanners if they were connecting into a national solution or if they were procuring their own local or regional solution. Also, 100 million is only a cost saving based on infrastructure and storage. We'd expect to see much more savings as part of the full-scale deployment of digital pathology. There obviously are lots of different deployment experiences that we've gone through. It's really difficult to try and list all of them, but I've just picked maybe the top 3 or 4 that are worth highlighting, I guess, from my perspective. So I guess the first one is to be careful of what the various suppliers promise, and always do your own research, speak to the sites or ask experts. Our experience shows that typically lots of sites don't have enough funding and have to reduce the amount of scanners or storage or infrastructure they can purchase. That's not necessarily a bad thing, but it's just important to be clear about expectations. What you don't want to do is find that you think you've budgeted for all the necessary components, and then get a surprise 6 months down the line when you're not in a position to be able to scan everything that you thought you would. I guess the second point is around resource management. The reason why I've added this is certainly within England and the deployments that we've been working on, there's been a lot of other projects and activities going on, which is fairly typical. But what it does mean is that a lot of the time the same staff are involved. And so we do have lab reconfiguration projects LIMS deployments, regional systems that are being deployed, as well as other IT projects, especially from an IT informatics point of view. And so trying to get hold of these key people is sometimes quite difficult, and usually requires a lot of escalation and prioritization of the work that needs to be done. And also a lot of the constraints are linked to this because especially if you've got connectivity issues, there's typically usually only one person that can really help you, and if they're on leave or if they're busy on other projects, then it means that your work will need to wait until that resource is available again. One of my favorite points to bring up is around having a great delivery team. It took us a while to recruit the relevant people into the team. Most of you within England will understand the challenges that there are around recruitment and retention. So I would put that up there in terms of key areas for consideration. And I guess, if you can bring together a great delivery team, that's cool. Or maybe you can just hire one. It's also worth taking the opportunity to thank the deployment team. The guys have been magnificent over the last couple of years, and clearly without their help, support, knowledge and expertise, we wouldn't have been able to go live with our national solution. So thanks. Alongside that, I'd add persistence and patience. Linked to a lot of the points that I've raised, due to competing priorities and people's availability, I would add those two words as key to being able to do a successful deployment. So continue your persistence, be patient, and eventually things will come to some fruition. And my final point is really a catch-all. If you guys haven't had the opportunity to go through or look at the Leeds Guide Volume 2, then I would certainly recommend you have a look at that. There's a broader set of deployment experiences, not just some IT areas, but looks at some of the lab work, some of the other factors, and it's certainly worth having the opportunity to go through that if you haven't done so already. So that can be found on the NPIC website, and there'll be a link in the description at the bottom. And just focusing on some of the technical challenges, what I would say at the start is the road to success is not easy, even though it might seem like that when you're there. I think what was key for us is finding a suitable supplier for infrastructure. The size and scale of what we wanted to do was typically outside of the scope of a traditional IT department. And so it's usually going to be critical for you to find someone who's going to be able to look after the IT infrastructure and storage components. Site-to-site connectivity is challenging, especially because there's lots of security-related things that need to be done. Firewalls, ports, antivirus software, all of those components tend to create connectivity issues. And what we would say is certainly look at dedicated site-to-site connectivity if you can afford that. Having integration between the LIMS is difficult, but with time it will become easier. And the reason why I say that is Currently, we have a mixture of hospitals using lab information systems that are really old and it's pretty impossible to integrate with, versus them being on a roadmap onto a new regional lab information system. But we might not be quite there yet, i.e., that project or program of work is still going. So typically, we've experienced that they're usually dependencies to the work that we're doing, and we simply have to try and integrate with what's there. And if we can't, then we typically would wait until that LIMS system is in place and do the integration work. One of the big challenges we had was, and I think there still is, a level of chip shortages. So when we were building our vast infrastructure, trying to get hold of certain components was very, very challenging. And so if you guys are looking at building infrastructure, then it's worth factoring in potential delays on getting component parts for your storage or for your virtual machines. And that was something that nearly caught us out, but thankfully our suppliers managed to pull through and mitigate any risk to our program. Existing trust-wide IT projects and prioritization. I kind of touched on that around resourcing, but again, there's lots going on within the NHS and lots going on within each hospital. And so trying to get your work prioritized is usually good. I guess the learning from us was we had a senior responsible owner who was supporting the program at an executive level. And I think getting that buy-in with the executive team early on in the program is vital for the program to hit the timelines and the plans that it set out. One of the other challenges is ensuring the tracking systems, the lab systems, and the packs work seamlessly. And what I would say is we're not there yet. There's still work that is ongoing to enable there to be much more seamless integration between certainly two of those systems. But it's work that will probably impact yourselves at some point over the course of your delivery. And I guess the final point is linked to standards. And what we feel is standards will aid interoperability issues and will support the ability for seamless transition between systems or sharing of images between different systems. And that pretty much brings me nicely onto the next presentation, which my colleague Dr. Craig Sayers will pick up, and hopefully he'll go into some discussions around DICOM within digital pathology. So I guess all that's left for me to say is thanks very much for listening. Hopefully you found some of the messages useful, and if you prefer to have some further dialogue, or if you've got some questions or queries, please drop them into the chat now, and I'll try and get back to you either through the QA session or after the event. So yeah, thanks for listening, guys, and hope you found this useful.
Hi, my name's Craig Sayers. I'm a consultant histopathologist at the Mid Yorkshire Hospitals NHS Trust, and I'm also the clinical lead for standards and interoperability for NPIC. I'm going to talk to you today briefly about DICOM. Although I'm no technical expert on DICOM, but hopefully I'm going to share with you what I've learned over the last couple of years and give you a bit more of an insight into this format. This is an outline of the presentation. We'll start by briefly discussing the importance of DICOM in the NPIC project itself, and then move on to a basic overview of DICOM and its use in digital pathology. And we'll look at the current state of DICOM, both advantages and disadvantages, before a brief summary. Given that my experience of DICOM is through work with NPIC, we'll start with a brief overview of why we feel DICOM is important to this project. Main reasons why DICOM is important in the NPIC project are summarised in this one slide. Central to the storage of digital images in the project is the vendor-neutral archive, at the heart of which will be the DICOM format. As its name suggests, this means it's not tied into a single manufacturer or system, and it covers the need for scalability and future-proofing. The same archive can be used by any scanner, any software, and any AI tool if it's configured correctly. And the table on the left just summarises some of the current NPIC partners engaged at each sort of stage of the project. From the outset, partners were engaged on the understanding of this need for standardisation, and we had a bold statement that DICOM compliance is an entry criterion for NPIC. So that was a brief summary of the importance of DICOM in the NPIC project, but what is DICOM all about? So let's start with the basics of DICOM. The term DICOM stands for Digital Imaging and Communications in Medicine, and the definition from the DICOM website is the international standard for medical images and related information. It defines the formats for medical images that can be exchanged with the data and quality necessary for clinical use. DICOM originated in radiology in the 1980s. In the very early days of digital radiology, imaging devices from different vendors produced proprietary file formats only compatible with their own PACS, that's picture archiving and communication systems, and viewers, which made it practically impossible for radiology departments to replace their PACS with one from a different vendor without also exchanging all of their equipment. The DICOM standard was first published in 1993, and compliance with this standard meant that radiology equipment produced images on a standardized format and communicated with standard protocols. It's since expanded to cover numerous medical specialities, and it's now implemented in almost every radiology, cardiology, imaging and radiotherapy device, and increasingly devices in other medical specialities, including ophthalmology, dentistry, dermatology, surgery, and now obviously digital pathology. These are covered by 34 working groups which develop and publish supplements to the standard pertinent to these different specialities. Here are a few key concepts of the DICOM standard. The standard itself incorporates firstly compressed pixel data, so the image itself as a single image or multiple frames in JPEG format. Secondly, metadata, which is very important in clinical and AI applications, which includes both patient identification and demographics, but also details about the acquisition of the image itself, particularly important in digital pathology, which we'll come back to later. And thirdly, DICOM is not simply a file format, it also includes a number of services, most of which involve transmission of data over a network, the roots of which are in radiology, but most can be utilised in digital pathology. Examples of these include the store service, which is used to send images or other objects to a PACS or workstation, the query or retrieve service, which enables a workstation to find lists of images and then retrieve them from a PACS system, and thirdly, the modality work service, which provides a list of imaging procedures that have been scheduled and includes details about the subject of the procedure, so the patient ID and demographics, the type of the procedure, so the equipment type, the procedure description, and the ordering of the procedure, such as the referring physician or accession number. An image acquisition device, such as a CT scanner or a slide scanner in digital pathology, queries a service provider, such as the radiology information system or the LIMS system in digital pathology, to get this information, which is then used to populate details in the image metadata. Prior to the use of this service in radiology, the scanner operator was required to manually enter all the relevant details, which caused obvious issues with accuracy and completeness of information. Next, we'll look at how DICOM developed to encompass digital pathology. We've already mentioned the DICOM working groups. The specific working group for digital pathology is number 26. This group has been instrumental in the development of the standard for digital pathology, firstly by the production of these two DICOM supplements. These mapped out the amendments required to the DICOM standard for use in digital pathology. The specific supplements are 122 in 2008 and 145 in 2009. I'm not going to go into too much detail about these, but for those who are more technically minded, they're both available in full on the DICOM website. But a published standard such as these is not much use unless it's actually taken up and used by vendors and manufacturers and can be demonstrated in real-world usage. So this was the second part of the fundamental input from this working group, were the so-called connectathons. There were 5 of these events held between 2017 and 2019, at which there was active participation by a number of hardware and software vendors, the names of some of which are shown on this slide. So these ranged from the manufacturers of the scanners themselves, I'm sure you'll recognise some of the names on the right-hand box there, through to the actual software vendors for the viewing and analysis of the images, and also the archiving. These connectathons were held at digital pathology conferences such as Pathology Visions in the US and the European Congress on Digital Pathology, and were overall a great success. They were able to demonstrate to other vendors, manufacturers, and also clinicians and members of the public attending the events that the vendors were willing to work together with their competitors on this unified standard, and they were actually able to provide real-time side-by-side demonstrations at these conferences. There are a number of fundamental differences between imaging in radiology and digital pathology that require a different approach, and it's probably useful to mention some of these at this point. Firstly, whole slide images are very large in terms of the file size. It does vary, but with compression for a whole slide image, we're talking in the region of 300 to 500 megabytes. But this can be much larger depending on the maximum scanning resolution or whether the more complex Z-plane scanning is used, and this may lead to issues with storage and network capabilities. The standard also allows elements much more specific to histopathology. For example, it allows categorization by specimen rather than study or sort of examination type, which is more common in radiology. It allows details of the specimen processing description to be recorded, such as collection, fixation, embedding, and staining, which may become much more relevant in particular AI applications as well as clinically. It allows color management, which again is more relevant in digital pathology as we're looking at full color images compared to a lot of monochrome images in radiology. It allows the storage of annotations, and by this we're not just talking about the standard annotations that a radiologist or a pathologist might make whilst looking at a digital image to sort of mark an area or do a measurement on the image itself, but more complex annotations such as that might be used in AI applications. For example, if an AI application is highlighting all of the nuclei in a particular area or a particular field of vision, it allows the precise recording of the outline of each of these nuclei as an annotation, and also allows structured reports. A major difference as well between radiology and pathology is the need in digital pathology for rapid pan and zoom to large degrees of magnification in order to emulate the function of a light microscope, which is not required in viewing standard radiology images. Within DICOM, for digital pathology, the image data is stored as separate tiles, which allows access to a smaller region of the image without having to load large amounts of data across a network, which I will now attempt to demonstrate. The simplest way to store a 2D image data within a file is the single frame organization, which is demonstrated here. This is where the data are stored in rows extending across the entire image. So in this diagram, the pixels are represented by purple squares extending on that top row from the top left to the top right. And then onto the next row once that row is full of pixel data. However, this has a major limitation. To view a small portion of the image, demonstrated here by the dark green square, a much larger portion of the image must be loaded, demonstrated by the light green rows. So although we're only looking at a portion of each of those rows, the entirety of the rows must be loaded in order to access that small dark green square of pixel data. In order to solve this problem in DICOM for whole slide imaging, the 2D image data is stored in tiles, which may be squares or rectangles represented as squares in this diagram, rather than rows of pixels. So again, in this diagram, the dark purple pixels in the top left, as you can see, are arranged in a square rather than rows going all the way across as in the previous slide. This is a more complicated way of storing image data, but it has the major advantage that compared with the single frame organization, to view a small portion of the image, again represented by a dark green square on this diagram, a much smaller portion of the image needs to be loaded, represented by the 4 light green squares, rather than the entire 5 rows of pixel data required in the single frame organization that we saw on the previous slide. So this addresses the problem of rapid panning or moving around a slide at a single magnification, but what about the rapid zooming? The solution proposed in the Working Group 26 supplements was tiled pyramids. The idea is that the whole slide image is composed of multiple images at different resolutions, and there's 4 of them in this diagram. There's the baseline highest resolution image at the base of the pyramid, and then 3 intermediate zoom levels as we go up the pyramid. And the altitude of the pyramid corresponds to the zoom level. So in terms of microscopy, it's low power at the top and high power at the bottom or base of the pyramid. Again, the green square with the thick black outline is the retrieved portion of the image at an arbitrary resolution level, somewhere between the highest resolution baseline image and the first intermediate level. And the shaded areas on the levels themselves represent the tiles that must be retrieved to show this portion of the slide and allow rapid zooming. In terms of the pyramid, the entire highest resolution layer is very large, so storing lower magnification layers for faster zooming takes negligible extra file space. With the versatility of DICOM, there's no set number of these intermediate levels and no set size of tiles. And the tiles themselves may be stored in 2 ways. Firstly, as tiled full, where an entire set of the tiles for a rectangular field is stored in a pre-specified order, or tiled sparse, in which the tiles can be anywhere and even overlap, but the position of each tile is explicitly specified and stored. With this method, not all tiles need to be present, so you don't, for example, need to include the white space beyond the tissue at all resolution levels. Rightly or wrongly, I equate this to looking at images on Google Maps, in that if you're looking at a particular area on Google Maps at a sort of low power, you don't need the entire high power image with all the details loaded in by your computer, but as you zoom down, the relevant areas are loaded at higher resolution. And it might be technically incorrect to think about it this way, but I think it is a helpful way of thinking about this pyramid arrangement. I think now is a good time to leave the more technical aspects of the DICOM format and consider some of the advantages and disadvantages of DICOM in its current state. Here's a list of a few advantages of DICOM in digital pathology. Firstly, as we've already alluded to, it prevents vendor lock-in and future-proofing of long-term storage. So the idea is that if your digital slides are stored in DICOM format, if in the future you needed to change any element of your process, such as the scanners themselves or the PACS viewer or the storage solution, having things in DICOM format should make life a lot easier rather than having to convert things from proprietary formats, if that's indeed possible. It also allows digital pathology to integrate into existing PACS or IT systems, which might be particularly important in procuring of digital pathology solutions, in that if it can be fitted into your existing radiology PACS system, that might be a big cost saving. Relevant to this, it allows collaboration across disciplines. So, for example, the radiology and digital pathology images might be stored from the same patient in the same PACS system, allowing interested clinicians to view them side by side, which could be particularly important in MDTs. DICOM has a proven performance in viewing images, so the end user, the reporting pathologist, should not notice any difference between the DICOM file and a proprietary format. As we've already said, not all of the area of a slide needs to be captured at the highest resolution, so-called sparse tiled images, which means that there's more efficient use of storage. And importantly, the metadata can be stored in the DICOM header, particularly important for AI applications, but also important clinically if you were sharing a particular digital slide with colleagues in a different hospital, for example. And lastly, the DICOM standard is flexible. Things like colour management, annotations, and even structured reports can all be stored within the standard itself. And obviously there may also be disadvantages. It has been reported that there's potentially slower scanning to DICOM. Obviously this depends on individual scanners themselves and how they handle the format, or extra steps in file creation, such that if a scanner doesn't natively output DICOM, that extra step may be required in converting the proprietary file to DICOM. There's also problems populating the DICOM header. This element requires integration with the laboratory information management or LIMS system in terms of identification and specimen preparation. And many of these LIMS systems currently do not support the modality worklist interface that has been so successful in radiology. So getting this data out of the LIMS system is problematic. The next was listed as an advantage, but it could also be considered as a disadvantage. The fact that DICOM standard is flexible may lead to issues in terms of which are mandatory and which are optional fields, and how these are populated and which must be populated. Could cause issues and confusion further down the line. And lastly, if existing PACS or IT systems are being utilised for digital pathology, they may need to adapt to handle the larger file sizes compared with radiology. So that's about all I've got to say on DICOM today. And just to finish with a summary, DICOM is a well-established international standard in medical imaging. And indeed it's becoming well established in digital pathology by increasing adoption by whole slide imaging vendors. And if there's one takeaway message from today's presentation, it would be just to think about DICOM, and really particularly if you're planning or procuring any digital pathology solution, please just discuss it and think about the future, and ask any potential vendors about their existing and future plans for DICOM implementation, because it's going to become increasingly important, particularly within the NHS, we're hoping in coming years. And particularly if we're talking about integration into existing PACS systems, obviously DICOM is well known in radiology, so people will have that at the forefront of their minds already. And DICOM is a flexible developing standard. There's opportunities to get involved. The working group 26 that we've already discussed has a broad range of members, including pathologists like myself, through to representation from the vendors and manufacturers themselves, and more technically minded people. So that's a way to get involved. And also IHE Palm, that's integrating a healthcare enterprise, pathology and laboratory medicine, who deal with sort of profiles in terms of the workflows of how different elements of the digital pathology equipment and processes talk to each other. So that's another way of getting involved in their working group. So that's the end of my presentation. Finally, just to acknowledge David Clooney and the other members of the DICOM Working Group 26, who very much helped me in understanding and learning about DICOM, and also to Darren Trainer and the other staff at NPIC. Thank you very much.